The following is a conversation with Katherine de Kleer, a professor of planetary science and astronomy at Caltech. Her research is on the surface environments, atmospheres, and thermochemical histories of the planets and moons in our solar system. Quick mention of our sponsors: Fundrise, Blinkist, ExpressVPN, and Magic Spoon. Check them out in the description to support this podcast. As a side note, let me say that this conversation and a few others, quite big ones actually, that are coming up were filmed in a studio where I was trying to outsource some of the work. Like all experiments, it was a learning experience for me. It had some positives and negatives. Ultimately, I decided to return back to doing it the way I was doing before, but hopefully with a team who can help me out and work with me long term. The point is, I will always keep challenging myself, trying stuff out, learning, growing, and hopefully improving over time. My goal is to surround myself with people who love what they do, are amazing at it, and are obsessed with doing the best work of their lives. To me, there's nothing more energizing and fun than that. In fact, I'm currently hiring a few folks to work with me on very small projects. If this is something of interest to you, go to lexfridman.com/hiring. That's where I will always post opportunities for working with me. This is the Lex Fridman podcast, and here is my conversation with Katherine de Kleer. Why is Pluto not a planet anymore? Does this upset you, or has justice finally been served?
So I get asked this all the time. I think all planetary scientists get asked about Pluto, especially by kids who would just love for Pluto to still be a planet. But the reality is, when we first discovered Pluto, it was a unique object in the outer solar system, and we thought, we were adding a planet to the inventory of planets that we had. And then over time, it became clear that Pluto was not a unique large object in the outer solar system, that there were actually many of these. And as we started discovering more and more of them, we realized that the concept of Pluto being a planet didn't make sense unless maybe we added all the rest of them as planets. So, you could have imagined actually a different direction that this could have gone, where all the other objects that were discovered in that belt, or at least all the ones, let's say, above a certain size, became planets instead of Pluto being declassified. But we're now aware of many objects out there in the outer solar system and what's called the Kuiper belt that are of the same size, or in some cases even larger than Pluto. So the declassification was really just a realization that it was not in the same category as the other planets in the solar system, and we basically needed to refine our definition in such a way that took into account that there's this belt of debris out there in the outer solar system of things with a range of sizes.
Is there a hope for clear categorization of what is a planet and not? Or is it all just gray area? When you study planets, when you study moons, satellites of those planets, is there lines that are that could be cleanly drawn, or is it just a giant mess? Is it all like a fluid? Let's say not mess, but it's like fluid of what is a planet, what is a moon of a planet, what is debris, what is asteroids, all that kind of.
So there are technically clear definitions that were set down by the IAU, the International Astronomy Union.
Is it size related? Like, what are the parameters based on?
So the parameters are that it has to orbit the sun, which was essentially to rule out satellites. Of course, this was a not very forward-thinking definition because it technically means that all extrasolar planets, according to that definition, are not planets. So it has to orbit the sun. It has to be large enough that its gravity has caused it to become spherical in shape, which also applies to satellites and also applies to Pluto. The third part of the definition is the thing that really rules out everything else, which is that it has to have cleared out its orbital path. And because Pluto orbits in a belt of material, it doesn't satisfy that stipulation.
Why didn't it clear out the path? It's not big enough to knock everybody out of the way?
And this actually is not the first time it has happened. So Ceres, when it was discovered, Ceres is the largest asteroid in the asteroid belt, and it was originally considered a planet when it was first discovered, and it went through exactly the same history, where people actually realized that it was just one of many asteroids in the asteroid belt region, and then it got declassified to an asteroid, and now it's back to a dwarf planet. So there is a lot of reclassification. So to me, as somebody who studies solar system objects, I just personally don't care. My level of interest in something has nothing to do with what it's classified as. So my favorite objects in the solar system are all moons. And frequently when I talk about them, I refer to them as planets because to me they are planets. They have volcanoes, they have geology, they have atmospheres, they're planet-like worlds. And so the distinction is not super meaningful to me, but it is important just for having a general framework for understanding and talking about things to have a precise definition.
So you don't have a special romantic like appreciation of a moon versus a planet versus an asteroid. It's just an object that flies out there and it doesn't really matter what the categorization is. Because there's movies about asteroids and stuff, and then there's movies about the moon. Whatever is a really good movie. There's something about moons that that's almost like an outlier. Like you think of a moon as a thing that's the secret part, and the planet is like the more like vanilla regular part. None of that? You don't have any of that?
No, I actually do. The moons are my favorite things in the solar system. And I think part of what you're saying, I agree from maybe a slightly different perspective, which is from the perspective of exploration. We've spent a lot of time sending spacecraft missions to planets. We had a mission to Jupiter, we had a mission to Saturn, we have plenty of missions to Mars and missions to Venus. I think that exploration of the moons in the outer solar system is the next frontier of solar system exploration.
The belt of debris, just real quick, that's out there. Is there something incredible to be discovered there? Again, we tend to focus on the planets and the moons, but it feels like there's probably a lot of stuff out there. And it probably, what is it? It's like a garbage collector from outside of the solar system, isn't it? Like, doesn't it protect from other objects that kind of fly in? And like it just feels like it's a cool... You know when you like walk along the beach and look for stuff and like look for it feels like that's that kind of place where you can find cool weird things. I guess in our conversation today, when we think about tools and what science is studying, is there something to be studied out there, or we just don't have maybe the tools yet, or there's nothing to be found?
There's absolutely a lot to be found. So the material that's out there is remnant material from the formation of our solar system. We don't think it comes from outside the solar system, at least not most of it. But there are so many fascinating objects out there. And I think what you've hit on is exactly right, that we just don't have the tools to study them in detail.
Got it.
But we can look out there and we can see there are different species of ice on their surface that tells us about, the chemical composition of the disk that formed our solar system. Some of these objects are way brighter than they should be, meaning they have some kind of geological activity. People have hypothesized that some of these objects have subsurface oceans. You could even stretch your imagination and say some of those oceans could be habitable. But we can't get very detailed information about them because they're so far away. And so I think if any of those objects were in the inner solar system, it would be studied intently and would be very interesting.
So would you be able to design a probe in that like very dense debris field, be able to like hop from one place to another? Is that just outside the realm of like, how would you even design devices or sensors that go out there and take pictures and land? Do you have to land to truly understand a little piece of rock? Or can you understand it from remotely, like fly up close and remotely observe?
You can learn quite a lot from just a flyby, and that's all we're currently capable of doing in the outer solar system. The New Horizons mission is a recent example, which flew by Pluto, and then they had searched for another object that was out there in the Kuiper belt, any object that was basically somewhere that they could deflect their trajectory to actually fly by. And so they did fly by another object out there in the Kuiper belt, and they take pictures and they do what they can do. And if you've seen the images from that mission of Pluto, you can see just how much detail we have compared to just the sort of reddish dot that we knew of before. So you do get an amazing amount of information actually from just essentially a high-speed flyby.
It always makes me sad to think about flybys, that we might be able to, we might fly by a piece of rock, take a picture, and think, oh, that looks pretty and cool and whatever, and that you could study certain like composition of the surface and so on. But it's actually teeming with life, and we won't be able to see it at first. And it's sad Because you know, like when you're on a desert island, you wave your hands and the thing flies by, and you're trying to get their attention, and they probably do the same. Well, in their own way, bacteria probably, right? But and we miss it. I don't know. Some reason it makes me. It's the FOMO. It's fear of missing out. It makes me sad that there might be life out there, and we're not in touch with it. We're not talking. Yeah. Well, okay. A sad pause, Russian philosophical pause. Okay. What are the tools available to us to study planets and their moons?
Oh my goodness, that is such a big question. So among the field of astronomy, so planetary science, broadly speaking, well, it falls kind of at the border of astronomy, geology, climate science, chemistry, and even biology. So it's kind of on the border of many things, but part of it falls under the heading of astronomy. And among the things that you can study with telescopes, like solar system moons and planets, the solar system is really unique in that we can actually send spacecraft missions to the objects and study them in detail. And so I think that's the kind of type of tool that people are most aware of, that's most popularized, these amazing NASA missions that either you fly by the object, you orbit the object, you land on the object, potentially you can talk about digging into it, drilling, trying to detect tectonic tremors on its surface. The types of tools that I use are primarily telescopes. And so my background is in astrophysics. And so I actually got into solar system science from astronomy, not from, a childhood fascination with spacecraft missions, which is actually what a lot of planetary scientists became planetary scientists because of childhood fascination with spacecraft missions, which is kind of interesting for me to talk to people and see that trajectory. I kind of came at it from the fascination with telescopes angle.
Right. So you like telescopes, not rockets, or at least you.
When I was a kid, it was looking at the stars and playing with telescopes that really fascinated me, and that's how I got into this. But telescopes, it's amazing how much detail and how much information you can get from telescopes today. You can resolve individual cloud features and watch them kind of shear out in the atmosphere of Titan. You can literally watch volcanoes on Io change from day to day as the lava flows expand. And then, with spectroscopy, you get compositional information on all these things. And it's when I started doing solar system astronomy, I was surprised by how much detail and how much information you can get even from Earth, and then as well as from orbit, like the Hubble Space Telescope or the James Webb.
So with the telescope, you can, how much information can you get about volcanoes, about storms, about sort of weather, just so we kind of get a sense, like what a resolution we're talking about?
Well, in terms of resolution, so on a given night, if I go and take a picture of Io and its volcanoes, you can sometimes see at least a dozen different volcanoes. You can see the infrared emission coming off of them and resolve them, separate them from one another on the surface, and actually watch how the heat coming off of them changes with time. And I think this time variability aspect is one of the big advantages we get from telescopes. So you send a spacecraft mission there and you get an incredible amount of information over a very short time period. But for some science questions, you need to observe something for 30 years, 40 years. Like, let's say you want to look at the moon Titan, which has one of the most interesting atmospheres in the solar system. Its orbital period is 29, 30 years. And so if you want to look at how its atmospheric seasons work, you have to observe it over that long of a time period. And you're not going to do that with a spacecraft, but you can do it with telescopes.
Can we just zoom in on certain things? Like, let's talk about Io, which is the moon of Jupiter.
Right.
Okay. It's like epic. There's like volcanoes all over the place. It's, from a distance, it's awesome. So can you tell me about this moon? And you're sort of a scholar of many planets and moons, but that one kind of stood out to me. So why is that an interesting one?
For so many reasons, but Io is the most volcanically active object in the solar system. It has hundreds of active volcanoes on it. It has volcanic plumes that go hundreds of kilometers up above its surface. It puts out more volume of magma per volcano than volcanoes on Earth today. But I think, to me, the reason that it's most interesting is as a laboratory for understanding planetary processes. So one of the broad goals of planetary science is to put together a sort of more general and coherent framework for how planets work in general. Our current framework, it started out very Earth-centric. We start to understand how Earth volcanoes work. But then when you try to transport that to somewhere like Io that doesn't have an atmosphere, which makes has a very tenuous atmosphere, which makes a big difference for how the magma degasses. For something that's really small, for something that has a different heat source, for something that's embedded in another object's magnetic field, the kind of intuition we have from Earth doesn't apply. And so broadly, planetary science is trying to broaden that framework so that you have a kind of narrative that you can understand how each planet became different from every other planet. And I'm already making a mistake. When I say planet, I mean planets and moons. Like I said, I see the moons as planets.
As planets. Yeah, I actually already noticed that you didn't introduce Io as a moon of Jupiter. You completely, you kind of ignored the fact that Jupiter exists. It's like, let's focus on the, yeah. Okay, so, and you also didn't mention Europa, which I think is is that the most famous moon of Jupiter? Is that the one that gets attention because it might have life?
Exactly, yeah.
Okay. But to you, Io is also beautiful. What's the difference between volcanoes on Io versus Earth? You said atmosphere makes a difference.
The heat source plays a big role. So many of the moons in the outer solar system are heated from gravitationally by tidal heating. And I'm happy to describe what that is.
Please.
Not.
What's tidal?
Yes. So tidal heating it's if you want to understand and contextualize planets and moons, you have to understand their heat sources. So for Earth, we have radioactive decay in our interior as well as residual heat of formation. But for satellites, tidal heating plays a really significant role, and in particular in driving geological activity on satellites and potentially making those subsurface oceans in places like Europa and Enceladus habitable. And so the way that works is if you have multiple moons and their orbital periods are integer multiples of one another, that means that they're always encountering each other at the same point in the orbit. So if they were on just random orbits, they'd be encountering each other at random places, and the gravitational effect between the two moons would be canceling out over time. But because they're always meeting each other at the same point in the orbit, those gravitational interactions add up coherently. And so that tweaks them into eccentric orbits.
What's an eccentric orbit?
So eccentric orbit or elliptical orbit, it just means non-circular, so a deviation from a circular orbit. And that means that, for Io or Europa, at some points in their orbit, they're closer to Jupiter, and at some points in their orbit, they're farther away. And so when they're closer, they're stretched out in a sense, but literally just not very stretched out, like a couple hundred meters, something like that. And then when they're farthest away, they're less stretched out. And so you actually have the shape of the object deforming over the course of the orbit. And these orbits are like just a couple of days. And so that, in the case of Io, that is literally sufficient friction in its mantle to melt the rock of its mantle. And that's what generates the magma.
That's the source of the magma. Okay, so why is Europa is, I thought there was like ice and oceans underneath kind of thing. So why is Europa not getting the friction?
It is. It's just a little bit farther away from Jupiter. And then Ganymede is also in the orbital resonance. So it's a 3-object orbital resonance in the Jupiter system. But we have these sorts of orbital resonances all over the solar system and also in exoplanets. So for Europa, basically because it's farther from Jupiter, the effect is not as extreme, but you do still have heat generated in its interior in this way, and that could be driving hydrothermal activity at the base of its ocean, which obviously would be a really valuable thing for life.
Cool. So it's like heating up the ocean a little bit.
heating up the ocean a little bit, and specifically in these like hydrothermal vents where we see really interesting life
Yeah.
evolve in the bottom of
Yeah.
Earth's oceans.
That's cool. Okay, so what's Io? What else? So we know the source is this friction, but there's no atmosphere. I'm trying to get a sense of what it's like if you and I were to visit Io. Like, what would that look like? What would it feel like? Is the entire thing covered in basically volcanoes?
So it's interesting because there's very little atmosphere. The surface is actually really cold, very far below freezing on the surface when you're away from a volcano. But the volcanoes themselves are over 1,000 degrees, or the magma when it comes out is over 1,000 degrees, and so
But it does come to the surface, the magma,
it does. Yeah.
in particular places. Whoa, that probably looks beautiful. So like, it's frozen, not ice. Like, what is rock? It's really cold rock, and then you just have this like, what does that look? What would that look like with no atmosphere? Would it be smoke? What does it look like? It's just magma, like just red, yellow, like liquidy things, or
It's black. It's black and red, I guess. Like think of the type of magma that you see in Hawaii. So different types of magma flow in different ways. For example, so in somewhere like Io, the magma is really hot, and so it will flow out in sheets because it has really low viscosity.
Mhm.
Um, and I think the lava flows that we've been having in Hawaii over the past couple of years are probably a decent analogy, although Io's magmas, lavas are even more fluid and faster moving.
how faster?
Um,
Like what? How fast? Like if you? By the way, sorry, through the telescope, are you tracking at what time scale? Like every frame is how far apart? If you're looking through a telescope, are we talking about seconds? Or we're talking about days, months? When you kind of try to get a picture of what the surface might look like, what's the frequency?
so it depends a little bit on what you want to do. I ideally every night, but you could take a frame every second and see how things are changing. The problem with that is that for things to change on a 1 second time scale, you to actually see something change that fast, you have to have super high resolution. The spatial resolution we have is a couple hundred kilometers, and so
Okay, got
things
it.
are not changing on those scales over 1 second unless you have something really crazy happening.
So if you get a telescope closer to Io, if you get or a camera closer to Io, would you be able to understand something? Is that something of interest to you? Would you be able to understand something deeper about these volcanic eruptions and how magma flows and just the rate of the magma? Or is it basically enough to have the kilometer resolution? Do you get a
No
sense?
way. We want to go there.
You want to go? You
Absolutely.
want to go to Io?
I mean, I don't want to go there personally, but I want to send a spacecraft mission there. Absolutely.
Why? Why are you scared?
Why am I scared?
Oh, you mean you don't? Like
I don't want to go there as a human.
as a human.
I
So
want to
humans-
send a robot there to
I'll
look
say-
at it, though.
This is again, everybody's discriminating against robots. This is not, but it's fine. But it's not hospitable to humans in any way, right? So it's very cold and very hot.
It's very cold. The atmosphere is composed of sulfur dioxide, so
Okay,
you
got
couldn't
it.
breathe it. There's no pressure. I mean, it's kind of all the same things you talk about. One talks about Mars, only worse. The atmosphere is still 1,000 times less dense than Mars's. And the radiation environment is terrible because you're embedded deep within Jupiter's magnetic field. And Jupiter's magnetic field is full of charged particles that have all come out of Io's volcanoes, actually. Jupiter's magnetic field strips all this material out of Io's atmosphere.
Mhm.
And that populates its entire magnetosphere. And then that material comes back around and hits Io and spreads throughout the system, actually. It's like Io is the massive polluter of the Jupiter system.
Okay, cool. So what does studying Io teach you about volcanoes on Earth, or vice versa? Is in the difference of the two? What insights can you mine out that might be interesting in some way?
Yeah, we try to port the tools that we use to study Earth volcanism to Io, and it works to some extent, but it is challenging because the situations are so different and the compositions are really different. When you talk about outgassing, Earth volcanoes outgas primarily water and carbon dioxide, and then sulfur dioxide is the third most abundant gas. And on Io, the water and carbon dioxide are not there. Right. Either it didn't form with them or it lost them. We don't know. And so the chemistry of how the magma outgasses is completely different. But the kind of one, to me, most interesting analogy to Earth is that, so Io, as I've said, it has these really low viscosity magmas. The lava spreads really quickly across its surface. It can put out massive volumes of magma in relatively short periods of time. And that sort of volcanism is not happening anywhere else in the solar system today. But literally every terrestrial planet and the moon had this, what we call very effusive volcanism early in their history.
Okay, so this is almost like a little glimpse into the early history of Earth.
Yeah.
Okay, cool. So what are the chances that a volcano on Earth destroys all of human civilization? Maybe I wanted to sneak in that question.
Yeah, a volcano on Earth.
Do you think about that kind of stuff when you just study volcanoes elsewhere? Because isn't it kind of humbling to see something so powerful and so hot, like so unpleasant for humans? And then you realize we're sitting on many of them here.
Right. Yeah. Yellowstone is a classic example. I don't know what the chances are of that happening. My intuition would be that the chances of that are lower than the chances of us getting wiped out by some other means. Okay. That in the time, that maybe it'll happen eventually, that there'll be one of these massive volcanoes on Earth, but we'll probably be gone by then by some other means. Not to sound bleak, but
it's very comforting. Okay, so can we talk about Europa? Is there so maybe can you talk about the intuition, the hope that people have about life being on Europa? Maybe also, what are the things we know about it? What are things to you that are interesting about that particular moon of Jupiter?
Sure. Yeah, Europa is, from many perspectives, one of the really interesting places in the solar system among the solar system moons. So there are a few. There's a lot of interest in looking for or understanding the potential for life to evolve in the subsurface oceans. I think it's fairly widely accepted that the chances of life evolving on the surfaces of really anything in the solar system is very low. The radiation environment is too harsh, and there's just not liquids on the surface of most of these things, and it's canonically accepted that liquids are required for life. And so the subsurface oceans, in addition to maybe Titan's atmosphere, the subsurface oceans of the icy satellites are one of the most plausible places in the solar system for life to evolve. Europa and Enceladus are interesting because for many of the big satellites, so Ganymede and Callisto, also satellites of Jupiter, also are thought to have subsurface oceans. But they have these ice shells, and then there's an ocean underneath the ice shell. But on those moons, or on Ganymede, we think that there's another ice shell underneath, and then there's rock. And the reason that is a problem for life is that your ocean is probably just pure water because it's trapped between two big shells of ice. So Europa doesn't have this ice shell at the bottom of the ocean, we think. And so the water and rock are in direct interaction. And so that means that you can basically dissolve a lot of material out of the rock. You potentially have this hydrothermal activity that's injecting energy and nutrients for life to survive. And so this rock-water interface is considered really important for the potential habitability.
As a small aside, you kind of said that it's canonically assumed that water is required for life. Is it possible to have life like in the volcano? I remember people were like a National Geographic program or something kind of hypothesizing that you can really have life anywhere. So as long as there's a source of heat, a source of energy, do you think it's possible to have life in a volcano, like no water?
I think anything's possible.
It's
I
one of
think
those.
so. Water, it doesn't have to be water. That's sort of, you can tell as you identified, I phrased that really carefully. It's canonically
Yeah.
accepted that because we recognize that, scientists recognize that we have no idea what broad range of life could be out there. And all we really have is our biases of life as we know it. But for life as we know it, it's very helpful to have, or even necessary to have some kind of liquid, and preferably a polar solvent that can actually dissolve molecules, something like water. So the case of liquid methane on Titan is less ideal from that perspective. But, liquid magma, if it stays liquid long enough for life to evolve, you have a heat source, you have a liquid, you have nutrients. In theory, that checks your three classic astrobiology boxes.
That'd be fascinating. I mean, it'd be fascinating if it's possible to detect it easily. How would we detect if there is life on Europa? Is it possible to do in a non-contact way from a distance through telescopes and so on? Or do we need to send robots and do some drilling?
I think realistically, you need to do the drilling. So Europa also has these long tectonic features on its surface where it's thought that there's potential for water from the ocean to be somehow making its way up onto the surface. And you could imagine some out there scenario where there's bacteria in the ocean. It's somehow working its way up through the ice shell. It's spilling out on the surface. It's being killed by the radiation, but your instrument could detect some spectroscopic signature of that dead bacterium. But that's, that's many ifs and assumptions.
That's a hope, because then you don't have to do that much drilling. You can collect from the surface.
Right, or
Skeletons
even,
of
I'm
bacteria.
thinking even remotely.
Remotely. Yeah. That's sad that there's a single cell civilization living underneath all that ice, trying to get up, trying to get out.
So Enceladus gives you a slightly better chance of that, because Enceladus is a moon of Saturn, and it's broadly similar to Europa in some ways. It's an icy satellite. It has a subsurface ocean that's probably in touch with the rocky interior, but it has these massive geysers at its south pole where it's spewing out material that appears to be originating all the way from the ocean. And so in that case, you could potentially fly through that plume and scoop up that material and hope that at the velocities you'd be scooping it up, you're not destroying any signature of the life you're looking for. But let's say that you have some ingenuity and can come up with a way to do that, it potentially gives you a more direct opportunity, at least, to try to measure those bacteria directly.
Can you tell me a little more on how do you pronounce it?
Enceladus.
Enceladus. Can you tell me a little bit more about Enceladus? Like, we've been talking about way too much about Jupiter. Saturn doesn't get enough love. No. Saturn doesn't get as much love. So what's Enceladus? Is that the most exciting moon of Saturn?
Depends on your perspective. It's very exciting from a astrobiology perspective. I think Enceladus and Titan are the two most unique and interesting moons of Saturn that definitely both get the most attention, also from the life perspective.
So what's more likely, Titan or Enceladus for life? If you were to bet all your money in terms of like investing, which to investigate, what are the difference between the two that are interesting to you?
Yeah, so the potential for life in each of those two places is very different. So Titan is the one place in the solar system where you might imagine, again, all of this is so speculative, but you might imagine life evolving in the atmosphere. So from a biology perspective, Titan is interesting because it forms complex organic molecules in its atmosphere. It has a dense atmosphere. It's actually denser than Earth's. It's the only moon that has an atmosphere denser than Earth's.
That's cool.
It's got tons of methane in it. What happens is that methane gets irradiated, it breaks up, and it reforms with other things in the atmosphere. It makes these complex organic molecules, and it's effectively doing prebiotic chemistry in the atmosphere.
While still being freezing cold?
Yes.
Okay. What would that be like? Would that be pleasant for humans to hang out there? It's just really cold?
There's nowhere in the solar system that would be pleasant for humans. It would be cold. You couldn't breathe the air.
But colonization-wise, if there's an atmosphere, isn't that a big plus? Or still a ton of radiation? Okay, so... Okay, so Titan, that's a really nice feature that the life could be in the atmosphere, because then it's that might be remotely observable, or certainly is more accessible if you visit. Okay, so well, what about Enceladus? So that would be still in the ocean.
Right, and Enceladus has the advantage, like I said, of spewing material out of its south pole so you could collect it. But it has the disadvantage of the fact that we don't actually really understand how its ocean could stay frozen, could stay globally liquid over the age of the solar system. And so there are some models that say that it's going through this cyclical evolution where the ocean freezes completely and thaws completely, and the orbit sort of oscillates in and out of these eccentricities. And in that case, the potential for life ever occurring there in the first place is a lot lower, because if you only have an ocean for 100 million years, is that enough time?
And it also means there might be mass extinction events if it does occur.
Right.
And it just freezes.
Yes.
Again, very sad, man. This is very depressing. All the like slaughter of life elsewhere. How unlikely do you think life is on Earth? So when you study other planets and you study the contents of other planets, does that give you a perspective on the origin of life on Earth? Which, again, is full of mystery in itself. Not the evolution, but the origin. The first springing to life. Like from nothing to life. From the basic ingredients to life. And I guess another way of asking it is, how unique are we?
Yeah, it's a great question. And it's one that just scientifically we don't have an answer to. We don't even know how many times life evolved on Earth, if it was only once or if it happened independently 1,000 times in different places. We don't know whether it's happened anywhere else in the universe, although it feels absurd to believe that we are the only life that evolved in the entire universe, but it's conceivable. We just have no real information. We don't understand really how life came about in the first place on Earth.
I mean, so if you look at the Drake equation, that tries to estimate how many alien civilizations are out there. Planets have a big part to play in that equation. If you were to bet money, in terms of the odds of origins of life on Earth, I mean, this all has to do with how special and unique is Earth. What you land in terms of the number of civilizations has to do with how unique the rare Earth hypothesis is. How rare and special is Earth? How rare and special is the solar system? Like, if you had to bet all your money on a completely unscientific question. Well, no, actually, it's actually rigorously scientific. We just don't know a lot of things in that equation. There's a lot of mysteries about that. And it's slowly becoming better and better understood in terms of exoplanets, in terms of how many solar systems are out there where there's planets, there are Earth-like planets. It's getting better and better understood. What's your sense from that perspective? How many alien civilizations out there?
So
0 or 1
you're
plus?
right that the equation is being better understood, but you're really only talking about the first 3 parameters in the equation or something. You know, how many stars are there, how many planets per star, and then we're just barely scratching the surface of what fraction of those planets might be habitable. The rest of the terms in the equation are like, how likely is life to evolve given habitable conditions? How likely is it to survive? All these things. There are all these huge unknowns. Actually, I remember when I first saw that equation, I think it was my first year of college, and I thought, this is ridiculous. This is A, common sense that didn't need to give a name, you know, and B, just a bunch of unknowns. It's like putting our ignorance together in one equation. But I've actually, now I understand this equation, it's not something we will ever necessarily have the answer to. It just gives us a framework for having the exact conversation we're having right now.
Mm-hmm.
And I think that's how it was intended in the first place when it was put into writing, was to give people a language to communicate about the factors that go into the potential for aliens to be out there and for us to find them. I would put money on there being aliens. I would not put money on us having definitive evidence of them in my lifetime.
Well, definitive is a funny word, because my sense is, this is the saddest part for me, is my sense in terms of intelligent alien civilizations. I feel like we're so self-obsessed that we literally would not be able to detect them, even when they're like in front of us. Like trees could be aliens, but just their intelligence could be realized on a scale, on a time scale or physical scale that we're not appreciating. Like trees could be way more intelligent than us. I don't know. It's just a dumb example. It could be rocks, or it could be things like I love this. This is Dawkins memes. It could be that ideas are like ideas we have. Like, where do ideas come from? Where do thoughts come from? Maybe thoughts are the aliens, or maybe thoughts is the actual mechanisms of communication in physics, right? This is like, we think of thoughts as something that springs up from neurons firing. Where the hell did they come from? And now, what about consciousness? Maybe consciousness is the communication. It sounds like ridiculous, but like, we're so self-centered on this space-time communication in physical space, using like written language, like spoken with audio, on a time scale that's very specific, on a physical scale that's very specific. So I tend to think that. But bacteria will probably recognize, like moving organisms will probably recognize. But when that forms itself into intelligence, most likely it'll be robots of some kind, because we won't be meeting the origins. We'll be meeting the creations of those intelligences. We just would not be able to appreciate it. And that's the saddest thing to me, that we're too dumb to see aliens. Like we kind of think like, look at the progress of science. We've accomplished so much. The sad thing, it could be that we're just like in the first 0.0001% of understanding anything. It's humbling.
I hope that's true, because I feel like we're very ignorant as a species, and I hope that our current level of knowledge only represents the 0.001% of what we will someday achieve. That actually feels optimistic to me.
Well, I feel like that's easier for us to comprehend in the space of biology, and not as easy to comprehend in the space of physics, for example, because we have a sense that like we have it. Like if you talk to theoretical physicists, they have a sense that we understand the basic laws that form the nature of reality, of our universe. But so there's much more like physicists are much more confident. Biologists are like, this is a squishy mess. We're doing our best. Physicists, but it'd be fascinating to see if physicists themselves would also be humbled by there being like, what the hell is dark matter and dark energy? What the hell is not just the origin of not just the Big Bang, but everything that happened since the Big Bang. A lot of things that happened since the Big Bang we have no ideas about, except basic models of physics.
Right. Or what happened before the Big Bang.
What happened before? Or what's happening inside a black hole? Why is there a black hole at the center of our galaxy? Can somebody answer this? A supermassive black hole? Nobody knows how it started. And they seem to be like in the middle of all galaxies. So that could be a portal for aliens to communicate through consciousness. Okay. All right, back to planets. What's your favorite, outside of Earth, what's your favorite planet or moon? Maybe outside of the ones. Well, first, have we talked about it already? And then if we did mention it, what's the one outside of that?
Oh gosh, I have to come up with another favorite that's not Io.
Oh, Io's the
Oh,
favorite.
absolutely.
Why is Io the favorite?
I mean, basically everything I've already said. It's just such an amazing and unique object. But on, I guess, a personal note, it's probably the object that made me become a planetary scientist. It's the first thing in the solar system that really deeply captured my interest. And when I started my PhD, I wanted to be an astrophysicist working on things like galaxy evolution. And sort of slowly, I had done some projects in the solar system, but Io was the thing that like really caught me into doing solar system science.
Okay, let's leave moons aside. What's your favorite planet? It sounds like you like moons better than planets. So let's
That's accurate. But the planets are fascinating. I think, I find the planets in the solar system really fascinating. What I like about the moons is that there's so much less that is known. There's still a lot more discovery space, and the questions that we can ask are still the bigger questions.
Gotcha.
Which, and maybe I'm being unfair to the planets because we're still trying to understand things like, was there ever life on Mars? And that is a huge question, and one that we've sent numerous robots to Mars to try to answer. So maybe I'm being unfair to the planets, but there is certainly quite a bit more information that we have about the planets than the moons. But I mean, Venus is a fascinating object. So I like the objects that lie at the extremes. I think that if we can make a sort of theory or, like I've been saying, framework for understanding planets and moons that can incorporate even the most extreme ones, then, those are the things that really test your theory and test your understanding. And so they've always really fascinated me. Not so much the nice habitable places like Earth, but these extreme places like Venus that have sulfuric acid clouds and just incredibly hot and dense surfaces. And Venus, of course, I love volcanism for some reason. And Venus probably has volcanic activity, definitely has in the recent past, maybe has ongoing today.
What do you make of the news? Maybe you can update it in terms of life being discovered in the atmosphere of Venus. Is that... Sorry. Okay. You have opinion. I can already tell you have opinions. Was that fake news? I got excited when I saw that. What's the final is there a life on Venus?
So the detection that was reported was the detection of the molecule phosphine. And they said that they tried every other mechanism they could think of to produce phosphine, and no mechanism worked. And then they said, well, we know that life produces phosphine. And so that was sort of the train of logic. And I don't personally believe that phosphine was detected in the first place.
Okay, so this is just one study, but I, as a layman, am skeptical a little bit about tools that sense the contents of an atmosphere, like contents of an atmosphere from remotely, and making conclusive statements about life.
Oh, yeah. Well, that connection that you just made, the contents of the atmosphere to the life, is a tricky one. And yeah, I know that claim received a lot of criticism for the lines of logic that went from detection to claim of life. Even the detection itself, though, doesn't meet the sort of historical scientific standards of a detection. It was a very tenuous detection, and only one line of the species was detected, and a lot of really complicated data analysis methods had to be applied to even make that weak detection.
Yeah. So it could be noise, it could be polluted data, it could be all those things, and so it doesn't meet the level of rigor that you would hope. But of course, I mean, we're doing our best, and it's clear that the human species are hopeful to find life.
Clearly, yes. Everyone is so excited about that possibility.
All right, let me ask you about Mars. So there's a guy named Elon Musk, and he seems to want to take something called Dogecoin there. First to the moon. I'm just kidding about the Dogecoin. I don't even know what the heck is up with that whole. I think humor has power in the 21st century, in a way to spread ideas in the most positive way. So I love that kind of humor because it makes people smile. But it also kind of it's like a Trojan horse for cool ideas. You open with humor, and you like the humor is the appetizer, and then the main meal is the science and the engineering. Anyway, do you think it's possible to colonize Mars or other planets in the solar system? But we're especially looking to Mars. Is there something about planets that make them very harsh to humans? Is there something in particular you think about? And maybe in a high, like big picture perspective, do you have a hope we do, in fact, become a multiplanetary species?
I do think that if our species survives long enough and we don't wipe ourselves out or get wiped out by some other means, that we will eventually be able to colonize other planets. I do not expect that to happen in my lifetime. I mean, tourists may go to Mars. People who commit years of their life to going to Mars as a tourist may go to Mars. I don't think that we will colonize it.
Is there a sense why it's just too harsh of an environment to like it's too costly to build something habitable there for a large population?
I think that we need to do a lot of work in learning how to use the resources that are on the planet already to do the things we need. So if you're talking about someone going there for a few months, so I'll back up a little bit. There are many things that make Mars not hospitable. Temperature, you can't breathe the air, you need a pressure suit. Even if you're on the surface, the radiation environment is, even in all of those things, the radiation environment is too harsh for the human body. All of those things seem like they could eventually have technological solutions. The challenge, the real significant challenge to me seems to be the creation of a self-sustaining civilization there. You can bring pressure suits, you can bring oxygen to breathe, but those are all in limited supply. And if we're going to colonize it, we need to find ways to make use of the resources that are there to do things like produce food, produce the air the humans need to keep breathing. Just in order to make it self-sustaining, there's a tremendous amount of work that has to be done. And people are working on these problems, but I think that's going to be a major obstacle in going from visiting, where we can bring everything we need to survive in the short term, to actually colonizing.
Yeah, I find that whole project of the human species quite inspiring. These like huge moonshot projects. I was reading something in terms of the source of food that may be the most effective on Mars, is you could farm insects. That's the easiest thing to farm. So we'd be eating like cockroaches if we're living on Mars, because that's the easiest thing to actually, as a source of protein. So growing a source of protein is the easiest thing as insects. I just imagine this giant, for people who are afraid of insects, this is not a pleasant, maybe you're not supposed to even think of it that way. It'll be like a cockroach milkshake or something like that.
Right. I wonder have people been working on the genetic engineering of insects to make them
more radiation friendly,
right, or pressure resistant or whatever, make them more.
What can possibly go wrong? What kind of cockroaches make them radiation resistant? They're already like survived everything. Plus, I took an allergy test. I'm in Austin, so there's like the allergy levels are super high there. And one of the things, apparently, I'm not allergic to any insects except cockroaches, which is hilarious. So maybe, well, I'm going to use that as, how people use an excuse that I'm allergic to cats to not have cats. I'm going to use that as an excuse to not go to Mars as one of the first batch of people.
Although I was going to ask, if you had the opportunity, would you go?
Yeah, I'm joking about the cockroach thing. And I would definitely go. I love challenges. I love things. I love doing things where the possibility of death is not insignificant,
Hmm.
because it makes me appreciate it more. De- Meditating on death makes me appreciate life. And when the meditation on death is forced on you because of how difficult the task is, I enjoy those kinds of things. Most people don't, it seems like. But I love the idea of difficult journeys for no purpose whatsoever except exploration, going into the unknown, seeing what the limits of the human mind and the human body are. It's like, what the hell else is this whole journey that we're on for? But it could be because I grew up in the Soviet Union. There's a kind of love for space, like the space race, the Cold War created. I don't know if still it permeates American culture as much, but especially with the dad as a scientist, I think I've loved the idea of humans striving out towards the stars always. Like from the engineering perspective, has been really exciting. I don't know if people love that as much in America anymore. I think Elon is bringing that back a little bit, that excitement about rockets and going out there. But so that's hopeful. But for me, I always loved that idea. From a alien scientist perspective, if you were to look back on Earth, is there something interesting you could say about Earth? Like, how would you summarize Earth? Like in a report, like Hitchhiker's Guide to the Galaxy. Like if you had to report, like write a paper on Earth, or like a letter, like a one pager, summarizing the contents of the surface and the atmosphere. Is there something interesting? Like, do you ever take that kind of perspective on it? I know you like volcanism, so volcanoes, that'll probably be in the report.
I was going to say that's where I was going to go first. There are a few things to say about the atmosphere, but in terms of the volcanoes, so one of the really interesting puzzles to me in planetary science is, so we can look out there, and we've been talking about surfaces and volcanoes and atmospheres and things like that, but that is just this tiny little veneer on the outside of the planet, and most of the planet is completely sort of inaccessible to telescopes or to spacecraft missions. You can drill a meter into the surface, but that's still really the veneer. And one of the cool puzzles is looking at what's going on the surface and trying to figure out what's happening underneath, or just any kind of indirect means that you have to study the interior, because you can't dig into it directly. Even on Earth, you can't dig deep into Earth. So from that perspective, looking at Earth, one thing that you would be able to tell from orbit, given enough time, is that Earth has tectonic plates. So you would see that volcanoes follow the edges. If you trace where all the volcanoes are on Earth, they follow these lines that trace the edges of the plates. And similarly, you would see things like the Hawaiian string of volcanoes that you could infer, just like we did as people actually living on Earth, that the plates are moving over some plume that's coming up through the mantle. And so you could use that to say, if the aliens could look at where the volcanoes are happening on Earth and say something about the fact that Earth has plate tectonics, which makes it really unique in the solar system.
Oh, really? So the other planets don't have
It's the only one that has plate tectonics. Yeah.
Well, what about Io and the friction and all that? That's not plate tectonics. What's the difference between... So, it's plate tectonics, like another layer of like solid rock that moves around, and there's cracks.
Exactly. Yeah. So Earth has plates of solid rock sitting on top of a partially molten layer, and those plates are kind of shifting around. On Io, it doesn't have that, and the volcanism is what we call heat pipe volcanism. It's the magma just punches a hole through the crust and comes out on the surface. I mean, that's a simplification, but that's effectively what's happening.
Through the freezing cold crust.
Yes. Very cold, very rigid crust. Yeah.
How does that look like, by the way? I don't think we've mentioned. So the gas that's expelled, like if we were to look at it, does it look beautiful or does it look boring?
The gas?
Like the whole thing, like the magma punching through
Oh my
the
gosh.
icy.
Yes, I'm sure it would be beautiful. And the pictures we've seen of it are beautiful. You have so the magma will come out of the lava, will come out of these fissures, and you have these curtains of lava that are maybe even a kilometer high. So if you looked at videos, I don't know how many volcano videos you've looked at on Earth, but you sometimes see a tiny, tiny version of this in Iceland. You see just these sheets of magma coming out of a fissure when you have this really low viscosity magma, sort of water-like, coming out at these sheets. And the plumes that come out, because there's no atmosphere, all the plume molecules are just, or plume particles, where they end up is just a function of the direction that they left the vent. So they're all following ballistic trajectories. And you end up with these umbrella plumes. You don't get these sort of complicated plumes that you have on Earth that are occurring because of how that material is interacting with the atmosphere that's there. You just have these huge umbrellas. And it's been hypothesized, actually, that so the atmosphere is made of sulfur dioxide, and that you could have these kind of ash particles from the volcano, and the sulfur dioxide would condense onto these particles, and you'd have sulfur dioxide snow coming out of these volcanic plumes.
And there's not much light though, right? So you wouldn't be able to, like, it would not make a good Instagram photo, because you have to, would you see the snow?
Sure. There's light. It depends.
Oh, okay. So you could still, okay.
Depends what angle you're looking at it, where the sun is, all the things like that. You know, the sunlight is much weaker, but it's still there.
It's still there. And how big is Io in terms of gravity? Is it smaller? Is it a pretty small moon?
It's quite a bit smaller than Earth, anyway.
It's smaller than Earth. Okay. Okay, cool. So they float out for a little bit.
Mm-hmm.
So it floats. Wow. No, you're right. That would be gorgeous. What else about Earth is interesting besides volcanoes? So plate tectonics. I didn't realize that was a unique element of a planet in the solar system. Because I wonder what. I mean, we experience it as human beings. It's quite painful because of earthquakes and all those kinds of things. But I wonder if there's nice features to it.
Yeah, so coming back to habitability again, things like tectonics and plate tectonics are thought to play an important role in a surface being habitable, and that's because you have a way of recycling material. So if you have a stagnant surface, everything, you use up all the free oxygen, everything reacts until you no longer have reactants that life can extract energy from. And so if nothing's changing on your surface, you kind of reach this stagnation point. But something like plate tectonics recycles material. You bring up new fresh material from the interior, you bring down material that's up on the surface, and that can kind of refresh your nutrient supply in a sense, or the sort of raw materials that the surface has to work with. So from a kind of astrobiologist perspective, looking at Earth, you would see that recycling of material because of the plate tectonics. You would also see how much oxygen is in Earth's atmosphere. And between those two things, you would identify Earth as a reasonable candidate for a habitable environment, in addition to, of course, the, pleasant temperature and liquid water. But the abundance of oxygen and the plate tectonics both play a role as well.
And also see like tiny dot satellites flying around and
sure,
rockets.
Yes.
I wonder if they would be able to. I really think about that. Like if aliens were to visit, I mean, would they really see humans as the thing they should be focusing on? I think it would take a while, right? Because it's so obvious that should. Because there's like so much incredible in terms of biomass. Humans are a tiny, tiny, tiny fraction. There's like ants. They would probably detect ants, right? Or they probably would focus on the water and the fish, because there's like a lot of water. I was surprised to learn that there's more species on land than there is in the sea. Like there's 90 to 95% of the species are on land.
On land, not in the sea.
Not in the sea. I thought like there's so much going on in the sea, but no, right. The variety that like the branches created by evolution, apparently it's probably a good answer from evolutionary biology perspective why land created so much diversity, but it did. So like the sea, there's so much not known about the sea.
about the oceans, but it's not diversity friendly. What can I say? It needs to improve its diversity. What can you
Do you think the aliens would come? I mean, the first thing they would see is, I suppose, our cities. Assuming that they had some idea of what a natural world looked like, they would see cities and say, these don't belong. Which of these many species created these?
Yeah, I mean, if I were to guess, it's a good question. I don't know if you do this when you look at the telescope, whether you look at geometric shapes, like if it's because to me, like hard corners, like what do we think is engineered? Things that are like have kind of straight lines and corners and so on. They would probably detect those in terms of buildings would stand out to them, because that goes against the basic natural physics of the world. But I don't know if the electricity and lights and so on. It could be. I honestly, it could be the plate tectonics. It could be like the volcanoes. That'd be okay. That's a source of heat, and then they would focus. They might literally, I mean, depending on how alien life forms are, they might notice the microorganisms before they notice the big. Like notice the ant before the elephant, because like there's a lot more of them. Depending what their measuring device, we think like size matters, but maybe with their tools of measurement, they would look for quantity versus size. Like, why focus on the big thing? Focus on the thing that there's a lot of. And when they see humans, depending on their measurement devices, they might see we're made up of billions of organisms. Like the fact that we're very human-centered. We think we're one organism, but that may not be the case. They might see, in fact, they might also see like a human city as one organism. Like, what is this thing that like clearly this organism gets aroused at night because the lights go on, and then it sleeps during the day. I don't know what perspective you take on the city. Is there something interesting about Earth or other planets in terms of weather patterns? So we talked a lot about volcanic patterns. Is there something else about weather that's interesting, like storms or variations in temperature, all those kinds of things?
Yeah, so there's sort of every planet and moon has a kind of interesting and unique weather pattern, and those weather patterns are really, we don't have a good understanding of them. We don't even have a good understanding of the global circulation patterns of many of these atmospheres, why the storm systems occur. So the composition and occurrence of storms and clouds and these objects is another one of these kind of windows into the interior that I was talking about with surfaces. One of these ways that we can get perspective and what the composition is of the interior and how the circulation is working. So circulation will bring some species up from deeper in the atmosphere of the planet to some altitude that's a little bit colder, and that species will condense out and form a cloud at that altitude. And we can detect, in some cases, what those clouds are composed of. And looking at where those occur can tell you how the circulation cells are, whether the atmospheric circulation is, say, coming up at the equator and going down at the poles, or whether you have multiple cells in the atmosphere. And I mean, Jupiter's atmosphere is just insane. There's so much going on. You look at these pictures and there's all these vortices and anti-vortices, and you have these different bands that are moving in opposite directions that may be giving you information about the deep in the atmosphere, physically deep properties of Jupiter's interior and circulation.
What are these vortices? What's the basic material of the storms?
It's condensed molecules from the atmosphere, so ammonia ice particles in the case of Jupiter. It's methane ice in the case of, let's say, Uranus and Neptune, and other species. You can kind of construct a chemical model for which species can condense where. And so you see a cloud at a certain altitude within the atmosphere, and you can make a guess at what that cloud is made of, and sometimes measure it directly. And, different species make different colors as well.
Oh, cool. Ice storms. Okay.
I mean, the climate of Uranus has always been fascinating to me because it orbits on its side and it has a 42-year orbital period. And so, with Earth, our seasons are because our equator is tipped just a little bit to the plane that we orbit in. So sometimes the sunlight's a little bit above the equator and sometimes it's a little bit below the equator. But on Uranus, it's like for 10 years, the sunlight is directly on the North Pole, and then it's directly on the equator, and then it's directly on the South Pole. And it's actually kind of amazing that the atmosphere doesn't look crazier than it does. But understanding how, taking, again, like one of these extreme examples, if we can understand why that atmosphere behaves in the way it does, it's kind of a test of our understanding of how atmospheres work.
So it like heats up one side of the planet for 10 years and then freezes it the next, like, and that you're saying should probably lead to some chaos, and it doesn't.
The fact that it doesn't tells you something about the atmosphere. So atmospheres have a property that surfaces don't have, which is that they can redistribute heat a lot more effectively.
Right. So they have a stabilizing, like self-regulating aspect to them, that they're able to deal with extreme conditions. But predicting how that complex system unrolls is very difficult, as we know about predicting the weather on Earth even.
Oh my goodness.
Even with the little variation we have on Earth.
People have tried to put together global circulation models. So, we've done this for Earth. People have tried to do these for other planets as well. And it is a really hard problem. So Titan, for example, like I said, it's one of the best studied atmospheres in the solar system, and people have tried to make these global circulation models and actually predict what's going to happen moving into sort of the next season of Titan, and those predictions have ended up being wrong. And so then, I don't know, it's always exciting when a prediction is wrong because it means that there's something more to learn, like your theory wasn't sufficient. Mm-hmm. And then you get to go back and learn something by how you have to modify the theory to make it fit.
I'm excited by the possibility of one day there'll be, for various moons and planets, there'll be like news programs reporting the weather with the fake confidence of, like, as if you can predict the weather. We talked quite a bit about planets and moons. Can we talk a little bit about asteroids?
For sure.
What's an asteroid, and what kind of asteroids are there?
So the asteroids, let's talk about just the restricted to the main asteroid belt, which is the region. It's a region of debris, basically, between Mars and Jupiter. And these sort of belts of debris throughout the solar system, the outer solar system, the Kuiper belt that we talked about, the asteroid belt, as well as certain other populations where they accumulate because they're gravitationally more favored, are remnant objects from the origin of the solar system. And so one of the reasons that we are so interested in them, aside from potentially the fact that they could come hit Earth, but scientifically, it gives us a window into understanding the composition of the material from which Earth and the other planets formed, and how that material was kind of redistributed over the history of the solar system. So the asteroids, one could classify them in two different ways. Some of them are ancient objects, so they accreted out of the sort of disk of material that the whole solar system formed out of, and have kind of remained ever since more or less the same. They've probably collided with each other, and we see all these collisional fragments. And you can actually look and, based on their orbits, say, like these 50 objects originated as the same object. You can see them kind of dynamically moving apart after some big collision. And so some of them are these ancient objects, maybe, that have undergone collisions. And then there's this other category of object that is the one that I personally find really interesting, which is remnants of objects that could have been planets. So early on, a bunch of potential planets accreted that we call planetesimals, and they formed with a lot of energy, and they had enough time to actually differentiate. So some of these objects differentiated into cores and mantles and crusts. And then they were subsequently disrupted in these massive collisions. And now we have these fragments, we think fragments floating around the asteroid belt that are like bits of mantle, bits of core, bits of crust,
wow, cool.
basically.
So it's like puzzle pieces that you might be able to stitch together, or I guess it's all mixed up, so you can't stitch together the original planet candidates, or is that possible? To try to see if they kind of. I mean, there's too many objects in there to.
I think that there are cases where people have kind of looked at objects, and by looking at their orbits, they say these objects should have originated together, but they have very different compositions. And so then you can hypothesize maybe they were different fragments of a differentiated object. But one of the really cool things about this is, we've been talking about getting clues into the interiors of planets. We've never seen a planetary core or deep mantle directly. Some mantle material comes up on Earth's surface and then we can see it. But, in sort of in bulk, we haven't seen these things directly. And these asteroids potentially give us a chance to look at what our own core and mantle is like, or at least would be like if it had been also floating through space for a few billion years and getting irradiated and all that. But it's a cool potential window or analogy into the interior of our own planet.
Well, how do you begin studying some of these asteroids? What, if you were to put together a study, what are the interesting questions to ask that are a little bit more specific? Do you find a favorite asteroid that could be tracked and try to track it through telescopes? Or do you, you have to land on those things to study it?
So when it comes to the asteroids, there's so many of them, and the big pictures or the big questions are answered. So some questions can be answered by zooming in detail on individual object, but mostly you're trying to do a statistical study. So you want to look at thousands of objects, even hundreds of thousands of objects, and figure out what their composition is, and look at, how many big asteroids there are of this composition versus how many small asteroids of this other composition, and put together these kind of statistical properties of the asteroid belt. And those properties can be directly compared with the results of simulations for the formation of the solar system.
What do we know about the surfaces of asteroids, or the contents of the insides of asteroids? And what are still open questions?
So I would say that we don't know a whole lot about their compositions. Most of them are small, and so you can't study them in such detail with telescopes as you could, a planet or moon. And at the same time, because there are so many of them, you could send a spacecraft to a few, but you can't really get a statistical survey with spacecraft. And so a lot of what has been done comes down to sort of classification. You look at how bright they are. You look at whether they're red or blue. Simply, whether their spectrum is sloped towards long wavelengths or short wavelengths. There are certain, if you point a spectrograph at their surfaces, there are certain features you can see, so you can tell that some of them have silicates on them. But these are the sort of, they're pretty basic questions. We're still trying to classify them based on fairly basic information in kind of combination with our general understanding of the material the solar system formed from. And so you're coming in with prior knowledge, which is that you more or less know what the materials are the solar system formed from, and then you're trying to classify them into these categories. There's still a huge amount of room for understanding them better. And for understanding how their surfaces are changing in the space environment.
Is it hard to land on an asteroid? Is this a dumb question? It feels like it would be quite difficult to actually operate a spacecraft in such a dense field of debris.
Oh, the asteroid belt. There's a ton of material there, but it's actually not that dense. It is mostly open space.
Okay.
So mentally do picture like mostly open space with some rocks. The problem is some of them are not thought to be solid. So some of these asteroids, especially these core mantle fragments, you can think of as sort of solid like a planet, but some of them are just kind of aggregates of material. We call them rubble piles, and so there's not necessarily.
Might look like a rock, but do a lot of them have kind of clouds around them, like a dust cloud thing, or like do you know what you're stepping on when you try to land on it? Like what are we supposed to be visualizing here? There's like very few have water, right?
There's some water in the outer part of the asteroid belt, but they're not quite like comets.
Okay.
In the sense of having clouds around them. There are some crazy asteroids that do become active like comets. That's the whole other category of thing that we don't understand. But their surfaces, I mean, we have visited some. You can, find pictures the spacecraft have taken of them. And we've actually scooped up material off of the surface of some of these objects. We're bringing it back to analyze it in the lab. And there's a mission that's launching next year to land on one of these supposedly core fragment objects to try to figure out what the heck it is and what's going on with it. But the surfaces, they're you can picture a solid surface with some little grains of sand or pebbles on it and occasional boulders, maybe some fine dusty regions, dust kind of collecting in certain places. But
is there this? Do you worry about this? Is there any chance that one of these fellas destroys all of human civilization by an asteroid kind of colliding with something, changing its trajectory, and then heading its way towards Earth?
That is definitely possible. And it doesn't even have to necessarily collide with something and change its trajectory. We're not tracking all of them. We can't track all of them yet. There's still
a lot of them.
People are tracking a lot of them, and we are doing our best to track more of them. But there are a lot of them out there, and it would be potentially catastrophic if one of them impacted Earth. Are you aware of this Apophis object? So there's an asteroid, a near Earth object called Apophis that people thought had a decent probability of hitting Earth in 2029 and then potentially again in 2036. So they did a lot of studies. It's not actually going to hit Earth, but it is going to come very close. It's going to be visible in the sky in a relatively dark, not even that dark, probably not visible from Los Angeles, but, and it's going to come a tenth of the way between the Earth and the moon. It's going to come closer, apparently, than some geosynchronous communication satellites.
Oh, wow.
So that is a close call, but people have studied it and apparently are very confident it's not actually going to hit us. But it was.
I'm going to have to look into this because I'm very sure what's going to happen if an asteroid actually hits Earth, that the scientific community and government will confidently say that we have nothing to worry about. It's going to be a close call. And then last minute, they'll be like, there was a miscalculation. They're not lying. It's just like the space of possibilities, because it's very difficult to track these kinds of things. And there's a lot of there's complexities involved to this. There's a lot of uncertainties that something tells me that human civilization will end with, we'll see it coming, and then last minute there'll be oops. We'll see it coming and we'll be like, no, it's threatening, but no problem. And last minute it'll be like, oops, that was a miscalculation, and then it's all over in a matter of like a week. But is there or just very positive and optimistic today? Is there any chance that Bruce Willis can save us in the sense that, from what you know about asteroids, is there something that you can catch them early enough to change volcanic eruptions, right? Sort of drill, put a nuclear weapon inside, and break up the asteroid or change its trajectory.
There is potential for that if you catch it early enough in advance. I think, in theory, if you knew 5 years in advance, depending on the object and how close of how much you would need to deflect it, you could deflect it a little bit. I don't know that it would be sufficient in all cases. And this is definitely not my specific area of expertise, but my understanding is that there is something you could do. But it also, how you would carry that out depends a lot on the properties of the asteroid. If it's a solid object versus a rubble pile. So let's say you planted some bomb in the middle of it and it blew up, but it was just kind of a pile of material anyway, and then that material comes back together, and then you kind of just have the same thing. Presumably its trajectory would be altered, but it's
like Terminator 2, when it's like the thing that just like you shoot it and it splashes and then it comes back together. It would be very useless. That's fascinating. But what's fascinating, I've gotten a lot of hope from watching SpaceX rockets that land. There's so much, it's like, oh wow, from an AI perspective, from a robotics perspective, wow, we can do a hell of an amazing job with control. But then we have an understanding about surfaces here on Earth. We can map up a lot of things. I wonder if we can do that some kind of detail of being able to have that same level of precision in landing on surfaces with as wide of a variety as asteroids have. So be able to understand the exact properties of the surface and be able to encode that into whatever rocket that lands sufficiently to, I presume humans, unlike the movies, humans would likely get in the way. Like it should all be done by robots. And like land, drill, place the explosive, that should all be done through control, through robots. And then you should be able to dynamically adjust to the surface. The flip side of that, for a robotics person, I don't know if you've seen these, it's been very heartbreaking. Somebody I know well, Russ Tedrick at MIT, led the DARPA robotics challenge team for the humanoid robot challenge for DARPA. I don't know if you've seen videos of robots on 2 feet falling. But you're talking about millions, several years of work with some of the most brilliant roboticists in the world, millions of dollars. And the final thing is a highlight video on YouTube of robots falling. But they had a lot of trouble with uneven surfaces. That's basically what you have to do with the challenge involves you're mostly autonomous with some partial human communication. But that human communication is broken up. Like you get a noisy channel. So humans can, which is very similar to what it would be like in humans remotely operating a thing on an asteroid. And so with that, robots really struggle. There's some hilarious, painful videos of like a robot not able to like open the door. And then it tries to open the door without like, it misses the handle. And in doing so, like falls. I mean, it's painful to watch. So like that, there's that, and then there's SpaceX. So I have hope from SpaceX, and then I have less hope from Bipedal Robotics. But it's fun to kind of imagine, and I think the planetary side of it comes into play in understanding the surfaces of these asteroids more and more. That forget sort of destruction of human civilization. It'd be cool to have like spacecraft just landing on all these asteroids to study them at scale, and being able to figure out dynamically whether it's a rubble pile or whether it's a solid objects. Do you see that kind of future of science maybe 100, 200, 300 years from now where there's just robots expanding out through the solar system, like sensors essentially? Some of it taking pictures from a distance, some of them landing, just exploring and giving us data. Because it feels like we're working with very little data right now.
Sure. I do see exploration going that way. I think the way that NASA is currently or historically has been doing missions, is putting together these really large missions that do a lot of things and are extremely well tested and have a very low rate of failure. But now that these sort of CubeSat technologies are becoming easier to build, easier to launch, they're very cheap, and NASA is getting involved in this as well. There's a lot of interest in these missions that are relatively small, relatively cheap, and just do one thing. So you can really optimize it to just do this one thing, and maybe you could build 100 of them and send them to different asteroids, and they would just collect this one piece of information from each asteroid. It's a kind of different, more distributed way of doing science, I guess. And there's a ton of potential there. I agree.
Let me ask you about objects, or one particular object from outside our solar system. We don't get to study many of these, right? We don't get stuff that just flies in out of nowhere from outside the solar system and flies through. Apparently there's been two recently in the past few years. One of them is Oumuamua. What are your thoughts about Oumuamua? So fun to say. Could it be space junk from a distant alien civilization, or is this just a weird shaped comet?
I like the way that's phrased. So Oumuamua is a fascinating object. Just the fact that we have started discovering things that are coming in from outside our solar system is amazing, and can start to study them. And now that we have seen some, we can design now, kind of thinking in advance. The next time we see one, we will be much more ready for it. Yeah. We will know which telescopes we want to point at it. We will have explored whether we could even launch a fast turnaround mission to actually get to it before it leaves the solar system. In terms of Oumuamua, yeah, it's, for an object in our solar system, it's really unusual in two particular ways. One is the dimensions, that we don't see natural things in our solar system that are kind of long and skinny. We see the things we see in our solar system don't deviate from spherical by that much. And then that it showed these strange properties of accelerating as it was leaving the solar system, which was not understood at first. So in terms of the alien space junk, as a scientist, I cannot rule out that possibility. I have no evidence to the contrary. However...
So you're saying there's a chance.
I cannot, as a scientist, honestly say that I can rule out that it's alien space junk. However, I see the kind of alien explanation as following this, the Sagan's extraordinary claims require extraordinary evidence. If you are going to actually claim that something is aliens, you need to carefully evaluate, one needs to carefully evaluate the other options and see whether it could just be something that we know exists that makes sense. In the case of Oumuamua, there are explanations that fit well within our understanding of how things work. So there are two hypotheses for what it could be made of. They're both basically just ice shards. In one case, it's a nitrogen ice shard that came off of something like Pluto in another solar system. That Pluto got hit with something and broke up into pieces, and one of those pieces came through our solar system. Okay. In the other scenario, it's a bit of a failed solar system. So our solar system formed out of a collapsing molecular cloud. Sometimes those molecular clouds are not massive enough, and they sort of collapse into bits, but they don't actually form a solar system. But you end up with these kind of chunks of hydrogen ice, apparently. And so one of those chunks of hydrogen ice could have got ejected and passed through our solar system. So both cases explain these properties in about the same way. So those ices will sublimate once they've passed the sun. And so as they're moving away from the sun, you have the hydrogen or nitrogen ice sublimating off the sunward part of it. And so that is responsible for the acceleration. The shape also, because you have all this ice sublimating off the surface, if you take something, the analogy that works pretty well here is for a bar of soap. Your bar of soap starts out sort of close to spherical, at least from a physicist perspective. And as you use it over time, you eventually end up with this long, thin shard because it's been just by sort of weathering, as we would call it. And so in the same way, if you just sublimate material off of one of these ice shards, it ends up long and thin, and it ends up accelerating out of the solar system. And so given that these properties can be reasonably well explained that way, we should be extremely skeptical about attributing things to aliens.
See, the reason I like to think that it's aliens is because it puts a lot of priority on us not being lazy, and we need to catch this thing next time it comes around. I like the idea that there's objects, it almost saddens me. They come out of the darkness really fast. They just fly by and go and leave. It just seems like a wasted opportunity not to study them. It's it's the easiest way to do space travel outside of the solar system. It's having the things come to us, right?
I like that way of putting it.
And it would be nice to just land on it. And first of all, really importantly, detect it early.
Yes.
And then land on it with a really nice spacecraft and study the hell out of it. And if there's a chance it's aliens, alien life, it just feels like such a cheap way, inexpensive way to get information about alien life or something interesting that's out there. I mean, I'm not sure if an ice shard from another planetary system will be interesting, but it very well could be. It could be totally new sets of materials. It could be tell us about composition of planets we don't quite understand. And it's just nice when, especially in the case of Oumuamua, I guess it was pretty close to Earth. It would have been nice to it's like, don't go there, they come to us. I don't know. That's what makes me that's what makes me quite sad. It's a missed opportunity.
Well, yeah, and whether you think it's aliens or not, it's a missed opportunity. But we weren't prepared, and we will be prepared for the next ones. And so there's been a movement in astronomy more towards what's called time domain astronomy. So kind of monitoring the whole sky all the time at all wavelengths. That's kind of the goal. And so we expect to detect many more of these in the future. Even though these were the first two we saw, our potential to detect them is only increasing with time. And so there will be more opportunities. And, based on these two, we now can actually sit and think about what we'll do when the next one shows up.
What it made me realize, I know I didn't really think through this, but it made me realize if there is alien civilizations out there, the thing we're most likely to see first would be space junk, my stupid understanding of it. And the second would be really dumb kind of, you could think of maybe like relay nodes or something, objects that you need to have a whole lot of for particular purposes of space travel and so on, like speed limit signs or something. I don't know, whatever we have on Earth, a lot of. That's dumb. It's not aliens in themselves. It's like artifacts that are useful to the engineering in the systems that are engineered by alien civilizations. So we would see a lot of stuff in terms of SETI, in terms of looking for alien life and trying to communicate with it. Maybe we should be looking not for smart creatures or systems to communicate with. Maybe we should be looking for artifacts, or even as dumb as space junk. It just kind of reframed my perspective of what are we looking for as signs? Because there could be a lot of stuff that doesn't have intelligence, but gives us really strong signs that there's somewhere is life or intelligent life. And that made me kind of, I know it might be dumb to say, but reframe the kind of thing that we should be looking for.
Yeah, it's so the benefit of looking for intelligent life is that we perhaps have a better chance of recognizing it. We couldn't necessarily recognize what an alien stop sign looked like.
That's true.
And maybe, the theorists or the people who sort of model and try to understand solar system objects are pretty good at coming up with models for anything. I mean, maybe Oumuamua was a stop sign, but we're clever enough that we could come up with some physical explanations for it. And then, we all want to go with the simplest possible. We all want to believe the sort of most skeptical possible explanation. And so we missed it because we're too good at coming up with alternate explanations for things.
Right. And it's such an outlier, such a rare phenomenon that we can't study, 100 or 1,000 of these objects. We had just one. And so the science almost destroys the possibility of something special being there. It's like Johnny Ive, this designer of Apple. I don't know if you know who that is. He's the lead designer. He's the person who designed the iPhone and all the major things. And he talked about, he's brilliant, one of my favorite humans on Earth and one of the best designers in the history of Earth. He talked about like when he had this origins of an idea, like in his baby stages, he would not tell Steve Jobs because Steve would usually like trample all over it. He would say, this is a dumb idea. And so I sometimes think of the scientific community in that sense because the weapon of the scientific method is so strong at its best that it sometimes crushes the out-of-the-box outlier evidence. We don't get a lot of that evidence because we don't have... we're not lucky enough to have a lot of evidence, so we have to deal with just special cases. And special cases could present an inkling of something much bigger, but the scientific method user tramples all over it. And it's hard to know what to do with that because the scientific method works. But at the same time, every once in a while, it's like a balance. You have to do 99% of the time, you have to do like scientific rigor, but every once in a while, this is not you saying, me saying, smoke some weed and sit back and think, I wonder, it's the Joe Rogan thing. It's entirely possible that it's alien space junk. Anyway.
Yeah, I think so. I completely agree. And I think that most scientists do speculate about these things. It's just, at what point do you act on those things?
Yeah.
So you're right that the scientific method has inherent skepticism. And for the most part, that's a good thing because it means that we're not just believing crazy things all the time.
Right.
But it's an interesting point that requiring that high level of rigor occasionally means that you will miss something that is truly interesting because you needed to verify it 3 times and it wasn't verifiable.
I also think like when you communicate with the general public, I think there's power in that 1% speculation of just demonstrating authenticity as a human being, as a curious human being. I think too often, I think this is changing, but I've been quite disappointed in my colleagues throughout 2020 with the coronavirus. There's too much speaking from authority as opposed to speaking from curiosity. There's some of the most incredible science that's been done in 2020, especially on the virology, biology side. And the kind of being talked down to by scientists is always really disappointing to me, as opposed to inspiring. Like there's a lot of uncertainty about the coronavirus, but we know a lot of stuff. And we speak from, scientists from various disciplines speak from data in the face of that uncertainty. And we're curious. We don't know what the hell is going on. We don't know if this virus is going to evolve, mutate. We don't know if this virus or the next one might destroy all of human civilization. You can't speak with certainty. In fact, I was on a survey paper about masks. Something I don't talk much about because I don't like politics. But we don't know if masks work. But there's a lot of evidence to show that they work for this particular virus. The transmission of the virus is fascinating, actually. The biomechanics of the way viruses spread is fascinating. If it wasn't destructive, it would be beautiful. And we don't know, but it's inspiring to apply the scientific method to the best of our ability, but also to show that you don't always know everything, and perhaps not about the virus as much, but about other things, speculate. What if, what if it's the worst case and the best case? And because that's ultimately what we are, descendants of apes that are just curious about the world around us.
Yeah, I'll just add to that, not on the topic of masks, but on the topic of curiosity. That's, I mean, I think that's astronomy and planetary science as a field are are unique because for better and for worse, they don't directly impact humanity. So, we're not studying virology to prevent transmission of, illness amongst humans. We're not characterizing volcanoes on Earth that could destroy cities. It really is a more curious and, in my opinion, playful scientific field than many. So for better and worse, we can kind of afford to pursue some of the speculation more because human lives are not in danger if we speculate a little bit too freely and get something wrong.
Yeah, definitely. In the space of AI, I am worried that we're sometimes too eager, speaking for myself, to flip the switch to on just to see what happens. Maybe sometimes we want to be a little bit careful about that because bad things might happen. Is there books or movies in your life, long ago or recently, that were inspiring, had an impact on you that you would recommend?
Yeah, absolutely. So many that I just don't know where to start with it. So I love reading. I read obsessively. I've been reading fiction and a little bit of nonfiction, but mostly fiction obsessively since I was a child and just never stopped. So I have some favorite books. None of them are easy reading. So I recommend them for somebody who likes an intellectual challenge in the books that they read. So maybe I should go chronologically. I have at least 3. Okay. I'm not going to go through 50 here, but
yeah, I'd love to also maybe ideas that you took away from the ones you mentioned.
Yeah, why they were so compelling to me. One of the first books that really captured my fascination was Nabokov's book Pale Fire.
Oh wow.
Are you familiar with it?
Mm-hmm.
So I read it actually for a class. It's one of the few books I've ever read for a class that I actually really liked. And the book it's in some sense a puzzle. He's a brilliant writer, of course. But the book is it's formatted like a poem. So there's an introduction, a very long poem, and footnotes. And you get partway through it before realizing that the whole thing is actually a novel, unless you sort of read up on it going in. But the whole thing is a novel, and there's a story that slowly reveals itself over the course of all of this. And kind of reveals this just fascinating character, basically, and how his mind works in this story. The idea of a novel also being a kind of intellectual puzzle and something that slowly reveals itself over the course of reading was really fascinating to me, and I have since found a lot more writers like that. A contemporary example that comes to mind is Kazuo Ishiguro, who's pretty much all of his books are like slow reveals over the course of the book, and nothing much happens in the books, but you keep reading them because you just want to know what the reality is that he's slowly revealing to you. The kind of discovery-oriented reading, maybe.
Mm-hmm. What's the second one?
Perhaps my favorite writer is Rainer Maria Rilke.
Wow.
Are you familiar
no, also
with
not
him?
Familiar. Your hidden ones. I mean, I know in the Book of Well, but no, I've never read Pale Fire. But Rilke, I've never. I know it's a very difficult read. I know that much.
Yeah, right. All of these are difficult reads. I think I read in part for an intellectual challenge. But Rilke, so he wrote one thing that might be characterizable as a novel, but he wrote a lot of poetry. He wrote this series of poems called the Duino Elegies that were very impactful for me personally, just emotionally. Which actually, it kind of ties in with astronomy in that there's a sense, in which we're all going through our lives alone. And there's just this sense of kind of profound loneliness in the existence of every individual human. And I think I was drawn to astronomy in part because the sort of vast spaces, the kind of loneliness and desolateness of space made the sort of internal loneliness feel okay, in a sense. It like gave companionship, and that's how I feel about Rilke's poetry. He turns the kind of desolation and loneliness of human existence into something joyful and almost meaningful.
Yeah, there's something about melancholy. I don't know about Rilke in general, but like contemplating the melancholy nature of the human condition that makes it okay. Like I tend to, from an engineering perspective, think that there is so much loneliness we haven't explored within ourselves yet. And that's my hope, is to build AI systems that help us explore our own loneliness. I think that's kind of what love is and friendship is somebody who in a very small way helps us explore our own loneliness. Like they listen. We connect, like two lonely creatures connect for a time. And it's like, oh, like acknowledge that we exist together, like for a brief time. But in a somewhat shallow way, I think, relative to how much it's possible to truly connect as two consciousnesses. So AI might be able to help on that front. So what's the third one?
Actually, I hadn't realized it until this moment, but it's yet another one of these kind of slow reveal books. It's a contemporary Russian-American writer named Olga Grushin, Grushin. Okay. And she wrote this just phenomenal book called The Dream Life of Sukhanov that I read this year, maybe it was last year for the first time. And it's just a really beautiful... This one you could call a character study, I think, of a Russian father coming to terms with himself and his own past as he potentially slowly loses his mind.
Slow reveal. Slow reveal of a lot.
Well, that's apparent from the beginning. I don't think it's a spoiler.
Decline into madness. Spoiler alert.
So all of these are really heavy. I don't know. I don't have anything lighter to recommend. Well, Ishiguro's the light version of this.
Okay. Oh, well, heavy has a certain kind of beauty to it in itself. Is there advice you would give to a young person today that looks up to the stars and wonders what the heck they want to do with their life? So career, science, life in general. You've, for now, chosen a certain kind of path of curiosity. What insights do you draw from that you can give as advice to others?
I think for somebody, I would not presume to speak to giving people advice on life and humanity overall, but for somebody thinking of being a scientist, so there are a couple of things. One sort of practical thing, which is career-wise, I hadn't appreciated this going into science, but you need to... So the questions you're working on and the techniques you use are both of very high importance, maybe equal importance for being happy in your career. If there are questions you're interested in, but the techniques that you need to use to do them are tedious for you, then your job is going to be miserable, even if the questions are inspiring. So you have to find... But if the techniques that you use are things that excite you, then your job is fun every day. So for me, I'm fascinated by the solar system, and I love telescopes. And I love doing data analysis, playing with data from telescopes, coming up with new ways to use telescopes. And so that's where I have found that mesh. But if I was interested in, the dynamical evolution of the solar system, how the orbits of things evolve, then I would need to do a different type of work that I would just not find as appealing. And so it just wouldn't be a good fit. And so it sort of seems like an unromantic thing to have to think about the techniques being the thing you want to work on also, but it really makes a profound difference for, I think, your happiness in your scientific career.
I think that's really profound. It's like the menial tasks. If you enjoy those, that's a really good sign that that's the right path for you. I think David Foster Wallace said that the key to life is to be unboreable. Like, so basically, everything should be exciting. I don't think that's feasible, but you should find an area where everything is exciting. I mean, depending on the day, but you can find the joy in everything, not just the big, exciting, quote unquote, things that everyone thinks is exciting, but the details, the repetitive stuff, the menial stuff, the stuff that takes years, the stuff that involves a lot of failure and all those kinds of things, and you find that enjoyable. That's actually really profound to focus on that. Because people talk about like dreams and passion and goals and so on, the big thing, but that's not actually what takes you there. It takes you there is every single day, putting in the hours, and that's what actually makes up life, is the boring bits. And if the boring bits aren't boring, then that's an exciting life. Let me because when you were talking so romantically and passionately about Io, I remembered the poem by Robert Frost. So let me ask you, let me read the poem and ask what your opinion is. It's called Fire and Ice.
Oh, yeah. I could almost recite this from memory.
Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if I had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So let me ask, if you had to only choose one, would you choose the world to end in fire, in volcanic eruptions, in heat and magma, or in ice, frozen over? Fire or ice?
Fire.
Excellent choice.
The sort of... I've always been a fan of chaos, and the idea of things just slowly getting cold and stopping and dying is just so depressing to me. So much more depressing than things blowing up or, burning or getting covered by a lava flow. Somehow the activity of it endows it with more meaning to me, maybe.
I've just now had this vision of you, in action films where you're walking away without looking back and there's explosions behind you, and you put on shades, and then it goes to credits. So, Katherine, this was awesome. I think your work is really inspiring. The kind of things we'll discover about planets in the next few decades is super cool. And I know you said there's probably not life in one of them, but there might be. And I hope we discover just that. And perhaps even on Io, within the volcanic eruptions, there's a little creature hanging on that we'll one day discover. Thank you so much for wasting all your valuable time with me today. It was really awesome.
Yeah, likewise. Thank you for having me here.
Thanks for listening to this conversation with Katherine de Kleer, and thank you to Fundrise, Blinkist, ExpressVPN, and Magic Spoon. Check them out in the description to support this podcast. And now, let me leave you with some words from Carl Sagan. On Titan, the molecules that have been raining down like manna from heaven for the last 4 billion years might still be there, largely unaltered, deep frozen, awaiting for the chemists from Earth. Thank you for listening, and hope to see you next time.